compatriot János Bolyai discovered the non-Euclidean geometries parallel with Nikolai Ivanovich Lobachevsky. And this is also very important because without the first non-Euclidean geometry, Einstein couldn't discover his general relativity theory. And I think this is also an occasion to remember János Bolyai. János Bolyai discovered also the so-called absolute geometry, that means independent of the axiom of parallels. And this was the very big idea because then geometry became the language of also other sciences, for example, topology and so on and so on. And this was also an occasion for me, a great pleasure, that my friend Egon Schulte undertook the first presentation in this session, just continuing his presentation today. And please, Egon, start your presentation.
Thank you very much, Jenő, for kind words and for the invitation to give a talk. Thanks. Thank you. And I'd like to talk about the classification of regular polytopes by topology, regular or chiral polytopes by topology. And so I'd like to start with a brief review. This is primarily about higher dimensional polytopes. And so a convex polytope is defined as a convex hull of finitely many points in Euclidean space. And one key observation is that they are topologically spherical. That means the facets of the polytope are topologically spherical, and also the vertex links are topologically spherical. And the whole object is globally also spherical. And in the classical theory, there are different ways of saying what it means for a convex for a polytope to be regular. And it turns out that the most flexible way to define regularity is through the flag transitivity of the symmetry group, so the group of all isometries that preserves the polytope. And I have to say what a flag is. It's a maximal chain of mutually incident faces. So in 3 dimensions, you have a vertex, an edge containing the vertex, and a 2-dimensional face containing the edge and the vertex. And saying that the symmetry group is flag transitive means that any 2 flags can be moved into each other by a symmetry of the polytope. So the polytope looks alike at all comparable places. And the classification is well known. In the plane we have the convex p-gons. That's the Schläfli symbol for the p-gon, p in parentheses. And in 3 space we have the Platonic solids, pq. P stands for the number of vertices in a face, so the faces are p-gons, q coming together at each vertex. So here, for example, is the icosahedron. And then, in higher dimensions, the situation becomes more complicated, and we have, in 4 dimensions, we have 6 regular polytopes, and they are the simplex, that means it's sort of the 4-dimensional version of the tetrahedron, the cross polytope, the 4-dimensional version of the octahedron, the cube, the 4-dimensional version of the ordinary cube, the 24-cell, called this way because it had 24 3-dimensional faces on the boundary. There's a 600 cell having 600 3-dimensional faces on the boundary, and a 120 cell. And these 6 together are the regular convex polytopes in 4 dimensions. And as you move up in dimension, there are only 3 regular polytopes in each dimension. They are the simplex, the cross polytope, and the cube. So the generalizations of the tetrahedron, octahedron, and cube. So here, for example, is a picture of the 24 cell, here of the 4D cube, projected down into, it's strictly speaking a picture of a Schlegel diagram, so projected down into 2 space, so to speak. Yeah, so this is obtained by placing yourself on one of the 3-dimensional faces of the cube, assuming that the cube is transparent and looking down. And what you see is this picture. And this picture here for the 24 cell is obtained in the same fashion. The 24 cell has 24 octahedral facets, and assuming that the 24 cell is transparent, so you just see the vertices and edges, what you see is, if you look down, it's this object, it's decomposed into 23 octahedra. And there's also the outer octahedron, that's the one on which you are standing if you're looking into this. So these are Schlegel diagrams of the 24 cell and the cube. And here is an example made from toothpicks by Emil Weston, that's a student of Barry Monson. It's 120 cells, quite an ambitious thing to construct. Okay, so how do we go about actually describing these convex polytopes? So the way to do this is to study the symmetry group, and here I've indicated how you would do that in 3 dimensions. You take your 3-dimensional cube, you dissect it barycentrically, and you take one of the simplices that come up in the barycentric subdivision, and then the generators for the symmetry group are the reflections in the walls of that simplex. So for example here, this triangle here, this triangle wall, gives you the generator rho naught. And so there are 3 generators, and you can write down certain presentations for the symmetry group. Here, rho naught, rho naught squared, rho 1 squared, rho 2 squared is equal to 1, and so on. And the same thing works also in 4 dimensions. The symmetry group of a convex regular polytope, PQR, is a Coxeter group. And the Coxeter group, so represented by this Coxeter diagram, where each node represents a generator. So now in 4 dimensions we have 4 generators. And here's a presentation that you would get. And so this was a very brief summary of the convex regular polytopes in 4 dimensions, in Euclidean space. Then there's also the theory of tessellations in Euclidean space. So in which way can you tell Euclidean space by polytopes? And if you look at, these are the familiar tessellations in the plane, and here on the floor you have the square tessellation, but you also have the triangle tessellation, the hexagonal tessellation. So the triangle tessellation has this symbol, 3, 6, 3 indicating that you have triangles, 6 that 6 come together at each vertex. And then, of course, you have in every dimension the cubical tessellation, that's sort of the standard tessellation. And then 4-dimensional space is again exceptional in that there are 2 additional tessellations, and one is by 24 cells. Yeah, so you can tile Euclidean 4 space with 24 cells, so with these objects that I showed you. And the other is with cross polytopes, or generalized octahedra. They also tile. And in hyperbolic space you have other possibilities. So now I want to transition from sort of the standard theory of regular convex polytopes to so-called abstract polytopes. And let me tell you what an abstract polytope is. So the idea here is that you extract sort of some combinatorial properties of convex polytopes and use them to define this concept of an abstract polytope. And that was introduced around 1980s by Danza and Grünbaum. And so let me describe that. So you should have in mind the set of all faces of a convex polytope. That's sort of used initially to define this. But there will be lots of other examples. So an abstract polytope P of rank n, so we are now calling it rank rather than dimension. An abstract polytope P of rank n is a ranked partially ordered set. So we have a partially ordered set, and there's a rank function on it. So we have the elements of rank 0 we call the vertices, the elements of rank 1 we call the edges, the element of rank 2 would be the two faces, and the element of rank n-1 would be the facets. And there are incidences between these faces of various rings. And so the defining properties are as follows. The first is a trivial condition, namely that there's a face of rank -1 and a face of rank n. It's sort of the empty set and the full polytope. And then the next is each flag has exactly the same number of elements in it. So that means a flag contains the least face, which is a -1 face, then a vertex, an edge, a two face, and all the way up to the n face. And this is sort of implicit in this description that there is a rank function. And then P is connected in a certain well-defined sense, and the most important property is the intervals in this rank pose set, partially ordered set, have diamond shape. So what it means is, if you have an I-1 face and an I+1 face that contains the I-1 face, there are two I faces between it. So that's exactly this condition, is sort of a thinness condition. That's a condition that you meet in convex polytopes. Sort of, in some ways, a very important condition. And we want to study again the most symmetric objects, as we wanted for the convex polytopes. And we call those regular abstract polytopes, or just regular polytopes. And now the definition is that the combinatorial automorphism group, there's no longer a geometric automorphism group, but there's a combinatorial automorphism group, that must be transitive on the flags. So, in other words, combinatorially, the structure looks alike at all comparable places. And we will also talk about chirality. I'll leave that for a moment. How do these structures look like? That's the question. The first is, in ranks 0, 1, and 2, there's nothing new. So you can still think of a rank 0 polytope as a point, of a rank 1 polytope as a line segment, so to speak, but considered combinatorially. You have vertices and an edge joining them. Of the two polytopes, you can still think as the sort of a convex polygon, considered just combinatorially, or as an infinite polygon. That means a tessellation on the line, considered combinatorially. But then it starts becoming interesting. In 3 dimension, the abstract polytopes, or abstract polyhedra, are essentially the maps on closed surfaces. So by a map, I mean a two-cell tessellation on a closed surface. And here, for example, we have a tessellation of the torus. And here's sort of the structure, how it is built in principle. You take a square tessellation of the plane and you make a suitable identification. So, for example, you take a 5x5 grid and you identify opposite edges, and that creates a torus. So this subject has a very rich history, going back to Klein, Duke, Coxeter, and Brahana. And some people, there are lots of activities here, some people working with the subject. And it turns out that the regular maps on the torus have been very well studied by Coxeter in particular. He enumerated them. So they all look like, for example, of type 4BC, they look like something like this. Yeah, so they're obtained from the square tessellation of the plane and making suitable identifications. And you can also take the triangular tessellation of the plane and make suitable identifications. But how does an object like this look like in rank 4? So how does a convex polytope look like combinatorially? There are the three-dimensional polytopes that you stick together in order to create the boundary of a convex 4 polytope. So you should expect, in this case, that you somehow take maybe regular maps or handle bodies. It's easier to maybe visualize it. A handle body where each handle body has a tessellation on the boundary, and you stick together these handle bodies in a way to create a rank 4 structure. So, for example, if you have how does a local picture for a 4 polytope of type 443 look like? So let me take you through this. So the facets would now be, say, torus maps of this type, for example. You take an S by S chessboard and you identify opposite faces. So now you have sort of a torus that's decomposed in an S by S manner. And for simplicity, maybe think of the whole thing as a solid torus. And now you have a whole bunch of these solid tori, and you have to stick them together to create a complex that's made up from solid tori. And so what would have to happen, for example, if you have, say, a torus of this kind, then along each square of the torus there must be exactly one other torus. And the Schläfli symbol would tell you that along each edge of a torus there must be 3 tori. So it's a very complicated structure, and in fact, if you look at the local picture of, say, one vertex in a structure like this, because of this particular Schläfli type, it must be, the local structure must be that of a cube. So in other words, there are 6 tori coming together at one particular vertex, and that would be the local structure. And so the question is, what can you actually say about these structures? Can you classify them? And so on. So there are lots of interesting questions, and that takes us sort of to the actual classification problem. If you investigate these abstract polytopes, and if you focus on the spherical structures, so structures that are locally spherical, that means where you actually, say in rank 4, where you actually stick together platonic solids, and so that the vertex links are all spherical, then it turns out this is essentially taking quotients of regular tessellations in spherical space, Euclidean space, and hyperbolic space. So in some sense, the locally the locally spherical case corresponds to taking quotients sort of in regular tessellation of the familiar spaces. And in the 1970s, Branko-Grunbaum suggested to look at these structures and look at abstract polytopes that are locally toroidal. So objects of the form that I've mentioned. And so, for example, in rank 4, this would mean that your facets are maybe given by an S by S chessboard, but folded into a cube, and they all have to fit together in a nice fashion. Can you actually classify this? And it turns out that you can. And so the first, I have to now summarize because it's too detailed in the description. So the first object the first problem was to classify all the regular toroids in any rank or in any dimension. Because sort of to do the classification that Coxeter did for the 2 torus, he classified all the regular maps on the 2 torus. So they are type 4, 4, 3, 6, and 6, 3. And that we were able to do this, and So that was joint work with Peter McMullen. And here, for example, you have a tessellation of a 3 by 3 torus. It's sort of a 3 by 3 by 3 grid. And if you do the identifications to get the 3 torus, you get a tessellation of the 3 torus by 27 cubes. And so this is one particular way to do this. So out of the cubical tessellation of space, there are 3 independent ways of actually building these regular toroids. And 3 in high dimension, in rank, yeah. And then there are also the exceptional tori, so obtained from the tessellation of 4-dimensional space. And there are just 2 ways to do this. Each way is sort of parameterized in a suitable way. So now that you understand what the torus tessellations are, then you want to look at the locally toroidal structures. So for example, in ranks 4, let me look at this. So for example, here, if I look at this first line, what this is supposed to represent is that we take a torus of type 4,4 with a certain parameter vector. This S stands for parameter vector, like 5,0, for example. And here the vertex figure is a cube. So we are trying to construct the universal object that you can build by putting together 5 times 5, so 5 by 5 tori, in such a way that you build a cubical vertex figure. So locally toroidal means that your facets must be tori or spherical, and the vertex figures must be tori and spherical. And it turns out that whenever you can build an object at all, then there is also a universal object that you can build. And the classification really means to find all the universal object that you can build. And so it's quite an elaborate story. And let me, for example, tell you, I don't really have a nice picture because they get infinitely difficult. So for example, suppose I want to take an S by S torus. Yes, an S by S chessboard, fold it into a torus. Now I take an infinite supply of those. Try to stick them together such that my vertex figure is a cube. So that always means every vertex lies with 6 tori. What is the regular object? There is a so what is a regular polytope that has this type of facets and this type of vertex figure, cubical vertex figure? And what is the largest such object? And when are they finite? When are we in the situation of the regular convex polytope situation or the regular tessellation situation where you have infinitely many elements? So that's the key question, and it turns out, as you would expect, it is true that only for very small parameter values can you actually expect that the whole thing closes up in a finite fashion. As soon as the parameters are big enough, then the universal object still exists, but is infinite. And so we have. So we have done. We have investigated all these different classes. Remember, there are quite a few actually that you have to look at. So this would be 443, 444, so to speak. Then 633, and so for example, one question could be, if you take an hexagonal torus of a certain type, and you want icosahedral vertex figures, what is the universal object that you can build? Yeah, so that it turns out that in this particular case, actually, there's only one way to do this, namely when the parameter vector is 2, 0. And in any case, so we have made a lot of progress, and so here, for example, is an interesting observation that was made by Grunbaum and also Coxeter and Shepard, namely when S is equal to 3 here, so if you have a 3 by 3 chessboard, then you can actually realize it also on the 3 sphere with 20 tori. So that's a very nice geometric realization question. And I think my time is pretty much up. I should say that we have, for most of these classes that I showed, so roughly 85%, I would say, we have actually classified the universal, we call those the universal regular polytopes. But there are still, for the others, there are still some open cases. And I think that's it.
Nice survey and also this report of the results. Is there any question, please? Please.
Just a naive question. Have I understood it correctly that in higher dimensions there are, the higher dimension larger than 4, there are less regular polytopes?
Yes.
And why is this so?
I mean, there's something called the Schläfli determinant, and that has to be positive. So you can actually, from the combinatorial data, you can write down a quadratic form. So as a Schläfli symbol, yeah? And if you have a Schläfli symbol, you can write down a quadratic form, and this quadratic form must be positive definite in order for this object to exist in Euclidean space. And then it turns out that only these 3 cases occur. Yeah, so you can also argue differently. If you have understood what the situation is in 4 dimensions, then if you have a Schläfli symbol in 5 dimensions, then the first 3 entries so the Schläfli symbol in 5 dimensions has 4 entries. And the first 3 entries must come from a 4 polytope, and the last 3 must come from a 4 polytope. So in other words, the 2 Schläfli symbols from the 4-dimensional faces and from the 4-dimensional vertex figure must superimpose on the middle 2 entries. And that already restricts the possibility very significantly. But it's ultimately this positive definite.
Only one question, please.
Question related to this. So are there any other known results in mathematics or even physics which are related to this specialty of dimension 4? Does this relate to other issues?
Yeah, I mean, these are, in Lie theory, for example, yeah, I mean, there's a Coxeter group theory. Yeah, so the symmetry group of these regular convex polytopes, they are reflection groups. And the reflection groups play a fundamental role in Lie theory. Lie algebras, Lie groups. Yeah, not all of them. I mean, for example, the icosahedron and the 120 cell, they're non-crystallographic, so they won't show up in Lie theory.
Roman, you?
Egon, so are there some 3 manifolds associated with these universal guys?
In some cases, yes.
And what is known about the topology of this? They are simply connected, I guess?
No, I mean, the 3 manifolds you get only in the sort of the traditional case, where you have locally spherical facets and vertex figures. But there are other ways in which you can actually build a 3 manifold. You can actually, when I said that I take a handle body and the tessellation of the handle body, I was actually cheating. It was just, so it's the other way. The structures themselves are just tessellations on surfaces. But you can sort of make this tessellation fill a handle body in more than one way. And so if you fill in these handle bodies in different ways, you can get tessellations of some 3 manifolds. But that's quite involved, actually.
Dear colleagues, now I think it's time to continue. Yeah, thank you again. And next speaker will be my colleague, Robert Kozma from the Technical University of Budapest. Some preliminary thing is necessary. title is in the picture, and the co-author is Jenő. So Szirmai also, our colleagues at the Technical University of Budapest. Jenő is also the advisor of Robert, and this is partly joint work with them. Please, Robert.
So first of all, I'd like to thank the organizers for the opportunity to present at this conference. So I'll be talking about some symmetries of hyperbolic ball packing problems. So first I'll give an outline of my talk. So first I'll explain to you what ball packing problems are. I'll give some preliminaries on hyperbolic geometry, the simplicial density function, and describe what these objects called horospheres are, which are important for the optimal packings. I'll give some of our results on non-uniqueness of optimal packings in three-dimensional hyperbolic space, and I'll talk about four-dimensional hyperbolic space, a conjecture of Laszlo-Fejes-Tóth for the optimal packing density. He conjectured it's about 69%, and then we were able to come up with a better packing with about 71.5% packing density. Okay, so first of all, a packing is an arrangement in some space of non-overlapping bodies, and a famous packing problem that recently has been settled is the Kepler conjecture in regular Euclidean 3 space, where Kepler had conjectured in the 1600s that the best possible packing arrangement in Euclidean 3 space of balls of equal size is around 74%. And then Gauss was able to prove this for regular packings, and then in 1998 Thomas Hales came up with a computer-assisted proof using a method suggested by Laszlo-Fejes-Tóth, and a proof for the irregular case as well. Okay, so then naturally the question arises, what happens in hyperbolic space? There are some difficulties. How do you even define packing density in hyperbolic space? In hyperbolic 2 space, it's not possible, but in higher dimensional hyperbolic spaces, we can consider regular tessellations with nice symmetries to define packing density and use those to come up with some nice packings. So here's a picture of János Bolyai, since I'm coming from Hungary. So he's the Hungarian who came up with non-Euclidean geometry together with Lobachevsky, independently. So Bolyai published in the appendix in 1832, one of the first instances where non-Euclidean geometry came up. So he synthetically constructed this. He said to a letter he wrote to his father that he created a new world out of nothing, and then Lobachevsky, his contemporary, had a similar result, but only for hyperbolic geometry a few years before. But even though Bolyai's result was published in the appendix in 1832, he originally wrote that down in 1822-23, so there's a question of precedence there. Okay, so there are many different models of hyperbolic geometry. Perhaps the most well-known are the Poincaré model and the Klein model. So the Poincaré model is a conformal model, but in the Poincaré model, convexity is severely distorted. But the hyperbolic symmetries are given by the Möbius transformations. Okay, since we'll be looking at regular packings where the fundamental domains are regular tetrahedra, but polyhedra, we'll be using the Klein model because it preserves convexity of the cells, but it has the trade-off that the angles are severely distorted. Okay, so first I want to mention this important theorem, so the theorem on simplicial packing density. So it's known that in a space of constant curvature, locally, the densest possible packing arrangement is given for a given radius, ball, R, if we arrange n plus 1, for n-dimensional space, if we arrange n plus 1 balls of the same radius at the vertices of a regular simplex, and actually in hyperbolic space, in hyperbolic free space, and as you increase R, the radius of the balls, the packing density will increase in the bigger and bigger simplices. Okay? This is known for hyperbolic free space, and the function dnr is called the simplicial density function. Maybe I can draw a picture here so you can imagine better what's going on. So in three-dimensional space, in hyperbolic space, in the Klein model, you have a sphere, and then you can have a regular tetrahedron inside. And then you can put a ball of radius r about each vertex. And the density of the intersection of the balls sum divided by the volume of the tetrahedron is locally the largest density you can get. And as you increase the size of this simplex, this packing density increases. And in hyperbolic space, in the limiting case, you get a totally asymptotic tetrahedron with 4 balls called Horoballs. There's a formal definition of a Horoball, but you can think of Horoballs as balls centered at infinity with infinite radius. And this gives, theoretically, the highest bound for packing. So this is a picture of a regular tetrahedron with some metric distortions and 4 Horoballs at each vertex. And luckily, in hyperbolic free space, the totally asymptotic tetrahedron tiles gives rise to the tiling with Schlafly symbol 336. So that means that the sides of the tetrahedron are well triangles, and it's a tetrahedron, so 3 triangles meet at each vertex, and then there's 6 triangles about each edge. Okay? So, well, I had some slides about regular plane tessellations. Luckily, Egon already talked about these and explained Schlafly symbols. So in the Euclidean plane, there are 3 types of tessellations you can have: the triangular lattice, the hexagonal lattice, and the square lattice. And in hyperbolic space, you can have infinitely many. If you think of the first entry in the Schlafly symbol as P and the second entry as Q, then as long as P and 1 over P and 1 over Q are smaller than or equal to 1/2, you can have a tessellation. And here are 2 examples. This is here the black one is the tessellation with Schlafly symbol 7-3, which means there's heptagons where 3 meet at each vertex, and the green is the dual tessellation. And similarly here, you have the tessellation back Schlafly symbol. Okay, so, well, right, so it makes sense to talk about Coxeter simplexes. So, a Coxeter simplex in n-dimensional space is a simplex where each of the dihedral angles is a submultiple of pi, so pi over n for some n. And then in hyperbolic space, we allow simplices which have vertices at infinity. These exist only for dimensions n from 2 to 9, and there's an only finite number of such simplices for n greater than 3. And then the volumes of all these simplices are known and they've been calculated. And we'll be using these simplices to find packings. So first, also describe a Coxeter group. So a Coxeter group is a group with presentation of the form like that, where it's a finitely generated group, and these exponents that you hear are entries of a Coxeter matrix, which is symmetric, and it has 1 in the diagonals. And well, the entries of the matrix are integers or infinity. And so a special class of Coxeter group are the Coxeter simplex reflection groups, which are groups where you take a Coxeter simplex and you reflect onto its sides. And so that means that the fundamental domain of the group will be a Coxeter simplex. And these give a discrete group of isometries of a space of constant curvature. And there's infinitely, well, they give regular tessellations for hyperbolic space. And then so we can use these regular tilings to define packing density in hyperbolic space. So the way we define packing density is that we'll be talking about Horoball packings. We place a Horoball at each of the ideal vertices, compute the volume of the intersection of the Horoball with respect to the fundamental domain simplex, and divide that by the volume of the simplex. And then this coincides with the Dirichlet-Voronoi cell density. And so if we perform this computation for the Coxeter tiling with Schlafly symbol 336, it's a result of Beretsky and Florian that we get the packing density upper bound for hyperbolic space, which is about 85%. Okay, and here's the picture again. Now, in hyperbolic space, any two Horoballs are the same. Well, they're isometric. There exists a hyperbolic isometry taking one to the other. So we can define the notion of Horoball type. So at each ideal point of hyperbolic space, there's a one-parameter family of Horoballs. Perhaps I'll show the animation. So, okay. Where's that? Okay, that's a bit big. Okay, so here you see one cell, a tetrahedral cell of this 336 tiling, and then in the middle there's a smaller orta scheme or simplex. That's the fundamental domain of one of the Coxeter groups involved in this construction. And then here, apart from the metric distortion, all Horoballs are of the same type. Their relative densities with respect to the fundamental domain are the same. And what you can do is you can start increasing the size of the Horoball at the top. Okay. Why is it not doing anything? Okay, well, that's unfortunate. So anyway, what's supposed to happen is I start increasing the size of this Horoball at the top so that it becomes tangent to the facet of the simplex opposite. So the relative density of this Horoball with respect to the simplex would increase and the relative densities would decrease, and then what you're supposed to see is that at the two limiting cases you have the optimal packing density of about 85%, and in all the cases in between you have smaller packing density. Okay. Okay, so here are the two cases. So you can obtain the optimal packing density with one Horoball type, or two Horoball types. And then if we look at the tiling 436 with the cube, then there are also two other realizations of the optimal Horoball packing. And these are the results that we came up with as Szirmai. Okay, so now comes the interesting part. So you can compute the matrices of the reflections on the sides of the simplex. You have 4 of them, and you can start generating the packing. So if you apply 2 generators to the fundamental domain, then you get more and more balls. And if I apply 5 generators, I can generate the packing layer by layer, and these are nice fractal images that look like the limit sets of Kleinian groups that you might be familiar with. So if there are some artists here, then this might be interesting in its own right. Okay. Oh, and there's one more layer. So these are the optimal packings in hyperbolic space. So the ones on the left are the Vlersky-Florian ones with one Horoball type, and the ones on the right are the new kinds with 2 types of Horoballs. Okay, so now let's talk briefly about 4-dimensional hyperbolic space. So Laszlo Fejes to the conjecture that the best packing density in 4-dimensional hyperbolic space is around 69%. So here's a list of all the Coxeter groups in 4-dimensional hyperbolic space. So there are a number of them. They're connected by edges, and the number of the edges tell you the index of the subgroup relation. And here there are ones with 2 stars and 4 stars. Those mean that these have 2 ideal vertices and 3 ideal vertices, and the ones with no stars have 1 ideal vertex. And then with Szirmai we found that there were 7 groups in which, if we do Horoball packings, then we can exceed the Fejes conjecture. So the optimal packing density of hyperbolic 4 space is between 71% and 73%. This figure comes from the simplicial packing density bound. Okay, so I'll quickly go through how the density is computed in 4 space using the S4 group. This group has 1 ideal vertex. So the first thing you do is you parameterize the simplex. So it has 1 ideal vertex. We place it at the point 1, 0, 0, 1. So we use the projective model for hyperbolic geometry. The first coordinate is the projective coordinate. And then you have 4 other coordinates for, the 4 spatial coordinates. And then once you pick the coordinates that satisfy the angle requirements for that simplex, you can find the normal vectors, the planes opposite each vertex. So this simplex has 1 ideal vertex, and we want to place the largest possible Horoball at that vertex, so we need to find the perpendicular foot of that vertex to the plane opposite that side. And so that can be computed like this. It's that number. And this is the equation of the largest possible Horoball, where S is equal to minus 1/9. That tells you which Horoball of the one parameter family it is, which is centered at the point 1, 0, 0, 0, 1. Okay, and then once we have the Horoball, we have to find the intersections of the Horoballs to the sides or the edges of the simplex. You find the length of, well, so in four-dimensional hyperbolic space, the figure you get is a tetrahedron, and these are the side lengths of the tetrahedron. And you can find the volume of the tetrahedron using the Cayley-Menger determinant, because this is a horospheric tetrahedron, and the intrinsic geometry of the horosphere is Euclidean. And using a classical formula by János Bolyai, you can find the area of the volume, the four-dimensional volume of the Horoball piece, to be this number here. And then if we divide that by the area, the volume of the simplex cell, we find that the packing density is 0.71. Okay, and so I'm running out of time, so I'll be quick. So this exceeds the conjecture by Laszlo Fejes-Tóth. And actually, if we do the same process for all the other Coxeter groups, then we notice that the optimal packing density comes up many, well, the conjecture, the best known packing density in hyperbolic force space comes up many times, and this is due to some subgroup relationship. And then also for the doubly and the triply asymptotic cases, you end up with the same density of 71%. Okay, and it's more difficult to show the cases where you have more than one Horoball type, but I won't get into that. And then so since we computed the packing density in one cell, we can now use the Coxeter group to generalize that density to all of hyperbolic space. And there's a picture of Coxeter and the optimal packings in hyperbolic free space to finish off. So that's it. Thank you.
Thank you, Robert. I add that you could read Robert's paper in the proceedings, and there is also other topics in that paper. But is there any question? Is there any question, please? Maybe then I comment then that this is a very unexpected result, that this very dense hyperbolic packing has more realization, and in dimension 4 they could give a better conjecture than Laszlo Fejes-Tóth gave, and this is also more realization, and this is a little bit unexpected situation. If you have some question, then thank you, begin. And now the chairman has to work a little bit then, and I ask you for some patience, please. My compatriot Jenő, which is a little bit report on our initiatives. We are working together with Jenő, Szirmai, István, Prok, a relatively long program which is related with the so-called fundamental polyhedron classification. And this is a relatively old story, started the classification of the 17 plane crystallographic groups, of course. And then Poincaré had a very big initiative related with just the hyperbolic plane geometric classification and also the three-dimensional situation. Poincaré modeled also the Bolyai Lobachevskian hyperbolic plane and space and so on. And later on, Boris Nikolaevich Delaunay give the general problem how to find the possible fundamental domains for three-dimensional crystallographic groups. This problem is also open now, no closed result, only partial results. Now this is my, this is clear. This is the abstract in the pen drive, of course, and I mentioned here the possible generalization. That means the crystallographic groups could be imagined also in non-Euclidean situation. Robert reported a little bit the hyperbolic geometry, but it turned out that we have 8 homogeneous geometries where the crystallographic situation can occur, and I can tell you, it is the last remark, a little bit, that we could imagine that the different phenomena in crystallography, as Fullerene's five-fold rotational symmetry and so on, it can be imagined that this is why the space could be also non-Euclidean in small size. This is an open question, of course, but I think that quasi-crystallography not so natural than imagine the non-Euclidean structure for small size structures here. There are also interesting new results. Here the Jenő Szirmai's presentation later in the Nil geometry. Nil is also a three-dimensional homogeneous geometry. We have this Thurston classification for the 8 homogeneous geometry, and we could investigate such problems for non-Euclidean situation, because some cases maybe we can check in the nature, and then we could have a better understanding or Euclidean space, if space Euclidean or other spaces. For example, this electromagnetic resonance, which measure our brain, this is very obviously Nil geometric situation, and so on. And I mention here, this is just the interesting phenomena in three-dimensional Nil geometry. We have a denser ball packing than in the Euclidean space. This is denser because one ball is surrounded by 14 other balls, and we can continue the structure in a Nil lattice. That means lattice is no more parallel transformation. Lattice is here as fixed point free groups for in some spaces, and our initiative, this was a little bit my initiative, that we could realize, we could give projective models for all 8 geometries, and this unified model gives us the opportunity to differ the different cases, of course, and we could compare also the similar situation here. This is some references, very small, of course. Later I can mention that I could construct very early a hyperbolic Fußball manifold, which is no other than the Fußball filling the hyperbolic space. I think, by the way, that Fullerenes could be derived also in this way. That means this hyperbolic Fußball could locally fill some space, and this could be also model for Fullerene structures and so on. Now this is some abstract, and now a little bit shorter, the other stories, the projective sphere. That means the projective plane is there, please. And if I took a point outer and I consider the rays here, then the rays interpret the points of the projective geometry. This is the ray, represent x, and these vectors, all these vectors represent the same point. That means you could imagine that one-dimensional higher, we could realize also the projective plane by linear space and the subspace structure, of course, and this could be generalized also to higher dimensions, of course. Higher dimensional situation is a little bit algebraic, of course, but the analogies are not so complicated. Then, this is a very rich model. That means points are rays, lines are two-dimensional spaces, and the subspace structure, of course. That means a little bit rich linear algebra. I can tell you that all the linear algebra you studied at the university can formulate to projective geometry, and so on. And now it is just a picture for the hyperbolic plane model, as Robert told you. That means the Klein model here as a circle, and if I consider an outer point, then I could direct vectors to points. Then the planes are lines for the hyperbolic geometry. There are some bounding planes and lines for the so-called infinite points of the hyperbolic plane, which are parallel in János Bolyai's and Lobachevsky's sense, of course. And at the same time, you could consider also the structure as a similarity structure. That means we can consider here the H2 geometry, and in the third direction, if you take the logarithm of the proportionality factor, then we could consider H2 cross R. R is the proportionality, logarithm of the proportionality factor, and then just at the same time we have the same model of this situation. And now it is a summary for you. The projective models of the Thurston geometry, it is a very large structure, of course. That means the 8 Thurston geometry have some group theoretical characterization. Subgroups are characterized here, also the invariant spaces and so on. That means we have a unified characterization, and the so-called scalar product, the signature of the scalar product, that the number of the plus 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 quadratic form, S3 is plus plus plus, H3 minus plus plus plus. That means it is just the algebraic characterization. There are also similar structures. For example, 0 plus plus plus, it is also for S2 cross R, and also H3 here, please. That means then we have another characterization for other places, and so on. This is a very, very rich characterization by projective geometry. And now comes the situations S2. This is the the three-dimensional space. We consider the two-dimensional sphere because of the surfaces. And as I told formerly, the R factor, it is just the proportionality factor. S will be bigger and bigger and the logarithm of this proportionality give us the R component, and then we can consider, of course, the direct product situation here, and so on and so on. And then the next is some interesting phenomena. Sorry to say, you are right, the PowerPoint is not the same as my imagination. Yes, that means differential geometry can work. The infinite, the so-called arc length square here, for example, ds2, it is a situation, and then we can derive the so-called projective parametrization here, and you could transform this also so-called spherical coordinates and so on. That means there is a machinery, very unified machinery by Riemannian geometry also for later cases. And then next is the geodesic curves. That means if I have the arc length square, that means the Riemannian metric, then the second order differential equation gives us the geodesic lines, of course, and then we could consider geodesic lines in different direction, of course, and orthogonally for these geodesic lines we shall define the sphere and ball and so on and so on, and this is relatively unified method, of course. This is the geodesic curve if we solve this differential equation, of course. And this is also some animation. You see the geodesic curves grow from the origin, of course. Yeah. And then, as I promised, this is the geodesic sphere. Not homogeneous in Euclidean sense, because all the model have the spherical symmetry, of course, and this point, the origin is out of the origin, of course, and so on. This is the profile of this geodesic sphere, and so on. That means you could imagine that we have a very nice picture, artificially very nice picture. I could offer the artist here, sculptures and others. This is, for example, a ball packing in S2 cross R. Similarly, as Robert told you, we can define also ball packing, very dense ball packing. The record dense packing is 0.85 for the optimal of the Thurston geometries, and so on and so on. And this ball packing can have different symmetry arguments and so on. And then comes the H2 cross R geometry. That means now we have the hyperbolic plane, and the R parameter is orthogonal for the hyperbolic plane, and so on. Again, the arc length square situation, differential geometry, of course. Again, the geodesic line, and a little bit later you can see also the geodesic ball and sphere, of course, and this is also some ball packing for H2 cross R geometry. Jenő Szirmai investigated this very thoroughly, and so on. And now this is the next geometry, SR to R, which is nothing but the 2 times 2 matrices with determinant 1. That means we have then three real parameters, and for 3 real parameters we can imagine a 3-dimensional space, of course. The projectivity can be defined here, please, such a parameter transformation, in that sense that the determinant will be translated here minus minus plus plus signature, which is u in the geometry here, and then we can consider this situation in the classical models. That means a circle, a disk, is a hyperbolic plane. If the gum fiber are parallel, then we get H2 cross R. If we twist the gum fiber, then we have SL to R geometry, as you see here in this side. And by the way, this is very interesting, is a joint discovery by Vienna colleagues here, Helmut Stahel, Rolf Riesinger, Hans Havlicek, dealt with this problem without any connection with SL to R geometry, of course, and so on and so on. And then this new geometry gives also the second order differential equation for geodesic lines, of course. We could solve this, colleagues, two Croatian colleagues, and Szabolcs Barnabás, Brigitta Szilágyi could realize this exactly, of course. Not all differential equation could be expressed exactly, of course. And then you could see a little bit also the other animations here. For example, geodesic curves in SL to R geometry. This is in the hyperboloid model, but for the animation we get also coordinate system here. And now this is the hyperboloid model. It is the so-called Leicht-Cone, as in Einstein relativity theory comes this also. And later we could define also the geodesic sphere. Please, this is the geodesic sphere in SL to R. You see here the light cone. That means SL to R will be a little bit the hyperbolic plane. Hypersolic plane, this is the horizontal plane here. Then some light cone. And this part, the time-like situation, give us the R component, but this is twisted. More detail is not necessary here, maybe, but you could see here the growing the ball from the geometry. Horizontal line is the hyperbolic distance, now one, and then the other is there. And it is very interesting situation. We have also the so-called covering space arguments. I'm not detailed here because it would be too long in this presentation here. And another phenomena, please, that the so-called translational curves. That means translation could give us, for a given direction point, we could look for the curve which have this translate of the original direction vector by a first order differential equation. As this is the dynamical system for this situation. And it's very interesting that in SL to R, the so-called translational curve is different from geodesic curves. And this is why we have also translational spheres and balls different from geodesics. And this is very interesting and important in some investigation. And now, please, it's also the translational curve. This is, by the way, line in the projective model. That means translational curves are more natural than the geodesics in this model. And we have also some interesting question. What is the difference and how we could describe these differences and so on. And we could define also the translational spheres and balls. And we could define also the packing of these balls, the density problems, and so on. Part solved this problem, also the drawing the so-called translational sphere, please. And then, yes, this is an animation, maybe it's interesting. And then I turn to the nil geometry, which is nearer Euclidean geometry, of course. That means Euclidean plane. It is the same as nil geometrical plane, but in the third direction we can apply a twist again, and this is just realized by Heisenberg matrices. You see this 3 times 3 x, y, z as 3 components for a space, A, B, C, 3 components for a point, and the translation is just the matrix product here. And you see here in this component that the addition is no more commutative. It is no commutative translation, and this is why we have the center parameter here, and we have a very, very different geometry later. And this is also some simulation here. Sorry to say it is not working again. We could write this all for projective formulation, of course, when for 3-dimensional projective sphere we apply 4 times 4 matrices, of course. This is again the so-called Riemann metric here, and then we could define again the differential equation for geodesic, and this is the geodesic piece. It's no more like this is a helix-like geodesic in Euclidean space, very complicated differential. It is some animation. Different the geodesics in this the vertical direction is just a Euclidean line, of course. Other are helix. Yes, and so on. And this is, please, the so-called horizontal plane is here a hyperbolic paraboloid, of course. And it will be the next initiative if we could give a transformation which make this hyperbolic paraboid for a plane, then we can define another model of nil geometry, and this was our initiative with Benedek Schulte with this starting ball packing. This is the usual, and this is the usual geodesic balls here. It is no more convex and no more symmetric in the original sense, and depends on the radius, of course. There are some animation if we rotate the plane section here. And now the geodesic ball packings. You see here that the planar situation is just the regular hexagonal packing in the plane. But in the third direction you have these poles. This is pole, please, here, and no more as usual. And then we could define also a ball packing where every ball have 14 neighbors, please, and János Pallagi and Benedek Schultz made this also for Wolfram animation, and so on. And this was the Neal geometry, this new interpretation, where we have this new geodesic lines. Of course, this is a matrix transformation also for the other concept. The essential things that the translational curve will be line, and the usual horizontal plane were hyperbolic paraboloid, not now plane, and also for other planes, and so on. This is the rotational formula as Euclidean rotation here, and so on. Again, the new differential equation for geodesic lines and spheres, the Levi-Civita connections, please, differential geometry is working here, and maybe a little bit shorter. This is the geodesic line here is also not line, of course. The translation curve became line. This is the geodesic sphere now in the new coordinate system, and this was the starting model here, which is related with some Dirichlet-Voronoi cell, Dirichlet-Voronoi cell, the next, which is hexagon over under, but others are pentagons, and so on. And finally, I mention only the Sol geometry, which have such a translation, please. That means the Z component are exponential here. This is very strange geometry, also with other colleagues' opinion. But we could define the same concepts. Sorry to say, the geodesic line equation is no more elementary. That means we could solve only numerically and not exact formula with elementary function. But the translational curve is the geodesic curve. Péter Mátyás produced some numerical solution, please. And later comes the so-called translational curve. These are relatively nice, and we could have also animation, and so on. And this is again the geodesic differential equation for geodesic curve. This is the translational sphere here. The form is very characteristic. You can create also the sculpture of this, please, and so on. And I think you see here also some animation for this. This is a sphere, please, in Sol geometry, no more similar to Euclidean situation. And this is very characteristic that Sol geometry in the plane very similar to the Minkowskian planes if the special relativity theory, but the metric will be then positive definite, that means very locally Euclidean, such a transformation formula and the animation give us very rich things, and this is the densest ball packing of Sol space. You have to imagine these are spheres, please, and the deformation of the space by the parameter is very characteristically, of course. And this is my tank. My son helped me to present this. Sorry to say, the computer is not also so interesting, and thank you very much for your kind. And yeah, pardon, now I am a chairman. If you have some questions, yeah, you are. Yeah, please, if you, I'm a little bit tired, but we could continue also in the break. Yes. Yes. Please.
Yes, this is sort of related to the question of crystal groups. You suggested there may be some practical application here related to crystallography. And what sort of natural objects would you find that would fit into your imagination here?
Please, the Nil crystallography, pardon, Nil crystallography is
Very near.
represented in this electromagnetic resonance situation. I'm very curious if we could define the physical situation where crystals could grow after such a geometry. It is not.
There is the Eisenberg group there.
Pardon?
There is the Eisenberg group usually.
Yes, it is the same.
application.
But you see, this is just the electronic resonance, but also in the crystallography.
Yes. The Eisenberg group plays a role in quantum information too.
Please, then I ask you for this information because I would be very grateful if I could see. Yeah, thank you. Thank you then. Yeah. Pardon?
As far as I understood, you considered analogs of some classical questions of packing problems for non-Euclidean geometries in the three-dimensional case.
Yeah.
How much the results depends on the model, or they are totally independent? I mean, it doesn't matter which model you take for a given geometry, or because if one wants to produce, say, some bounds, it's good to start with some model and to try some packing. This is how some bounds are produced. And are these results model dependent or they are model independent?
That means this. Of course, these Riemannian spaces can be described without any models.
They just exist, I understand.
Exist. I think our main initiative here to define a unified model which could change in some sense, then we have one geometry. Another change, we have another geometry. Then we can compare different geometries in a unified way. And it is also important that this gives us also a unified method for measure distances, angles, group parameters, and crystallography groups, how to define a linear transformation, of course. This is the things, and I would be very curious in this sense, because this model, we could compare then other models which is known. Yeah. Yeah, this is.
How are you defining a sphere in each of these geometries?
The sphere is of course always a geodesic line. Geodesic line and the arc length parameter, of course. The arc length parameter.
Emil, do I understand it well? So let's go to two-dimensional, because there things are clear. For instance, such a universal model is you take complex numbers, and either you take the whole complex plane, or the upper half plane, or Poincare sphere.
Yeah.
And what changes is how you measure distances and angles and so on.
This is known for dimension 2.
Yes, and you are trying to introduce something like that.
Yes.
Sort of universal model for dimension 3.
Yes, yeah, this is the reason.
Where there will be basically the same machinery can be used, but you just change matrices.
Yeah, very difficult later. The second presentation of it would be first the original program. It is just the 8 geometries, how to construct polyhedron, if exist, of course. And the existence is just depends on this linear transformation and the calculation, matrix formula, and very strong computer programs are behind, of course.
Basically, you follow Felix Klein idea.
Yeah.
What is geometry? A group of matrices.
Thank you for these nice questions. Yeah. Yeah. If there is any other, I think then thank you again.